Hello, chemistry students. Professor Sean McMahon here with our second half of Chapter 7. So with the first two lectures, our focus were balancing chemical equations, identifying the different types, predicting products for the different types of reactions based on groups and solubility rules. In the second part, we'll be doing calculations to determine how much of a product can be produced based on starting material. So for the next two lectures, we are focusing on quantities in chemical reactions. So first, to do calculations, we have to understand that it's pretty much impossible for us to physically count atoms. They're too small. So what we're going to do is we're going to do something similar to what occurs at a hardware store, which is we can count by weight. So we can count by weighing things. So in a hardware store, you can sell nails by the pound because you can determine the mass of one nail and how many pounds it is. And then based on the number of pounds, you can determine how many nails you have. But we'll also use a unit to count, but the unit of 12 is a little too small for atoms. And that's because because atoms are so small, we have a lot of atoms in a small space. So we're going to use a dozen, but it's going to be referred to as the chemist's dozen, which is the mole. So a mole is a rather large number. It's 6.022 times 10 to the 23rd. To give you an idea of how large of a number that is, 1 times 10 to the 3 is 1,000. 1 times 10 to the 6 is 1,000,000. 1 times 10 to the 9th is 1,000,000,000. 1 times 10 to the 12th is a trillion. So you can see a mole is a really big number, okay? And that's because atoms and molecules are so small, we need a big number to count them. So how are we going to quantify? The mass of a single atom is too small to weigh on a scale. So an example, the mass of a hydrogen atom is 1.673 times 10 to the negative 24 grams, okay? So we need a better unit to express large numbers. So 1 mole, 6.022 times 10 to the 23rd objects, is just like 12 objects when we say a dozen. And basically what 1 mole is, it's the same number of particles that there are in 12 grams of carbon-12, of the isotope carbon-12. So the isotope carbon-12, if we remember or look at the periodic table, the atomic number for carbon is 6. So it has 6 protons, 6 neutrons, and 12 grams of it, if I have this isotope, is 6.022 times 10 to the 23rd carbon atoms. 1 mole of atoms of any element equals the atomic mass from the periodic table. But we use, instead of atomic mass unit, right? So for mass number, we were saying atomic mass units. We're just going to convert that to molar mass grams per mole. So 1 atom of hydrogen weighs 1.01 AMU. But again, this is a really small number. So to make it have some relevance, we're going to change the unit from AMU to grams per mole. And once we do that, once we change the number on the periodic table, the unit from grams to mole, that basically means I have 1 mole of that element. And a mole is that very big number, 6.022 times 10 to the 23rd. So what does 1 mole look like? Well, a mole of copper atoms. Now these would have to be pre-1982, but that's what it would look like, 63.55 grams. 1 mole of helium atoms would have to weigh 4 grams. So remember, a dozen means 12, but a chemist's dozen, the mole, is 6.02 times 10 to the 23rd. And I can have 1 mole of atoms, 1 mole of molecules, 1 mole of ions. It doesn't matter. It means 6.022 times 10 to the 23rd. You can even have a mole of donuts, but that'd kind of be, I won't get into it, but yeah. So what we're going to do is we're going to convert moles to the number of atoms. Okay, how? How many atoms are in 42.67 moles of copper? Well, I have 42.67 moles of copper. I know in a mole of anything, there's what? 6.022 times 10 to the 23rd. So I want to make sure the unit of moles of copper are on the bottom. Copper is an element. It's not a compound, so there's no molecules. It's atoms. There's 6.022 times 10 to the 23rd atoms of copper in 1 mole. The unit of moles cancel, and I get the number of copper atoms. My final answer has 4 sig figs because that's what I started with. I'm not going to use that number. I'm using the 42.67. How many molecules are in 7.32 moles of sulfur dioxide? So sulfur dioxide, sulfur dioxide. The reason why I have the Greek prefix is this is a binary covalent, and I have nonmetal with nonmetal, so I can't use charges. So I need to have a prefix to tell me the correct ratio. But I start with 7.32 moles of SO2. I need to get rid of the unit of moles and go to a number. So I use Avogadro's number. 1 mole of SO2 is 6.022 times 10 to the 23rd molecules of SO2. My final answer has 3 sig figs because I'm using the number in the problem. How many moles of silver is 8.46 times 10 to the 24 atoms of silver? Okay, so now I want to find moles instead of the number of atoms. Well, that's fine. I start with the number of atoms. I want to go to moles. I know 1 mole of anything is 6.022 times 10 to the 23rd atoms, so that goes on the bottom. The units of atoms cancel. I'm left with 14 moles of silver. I have 3 sig figs here, so I have 3 sig figs here. And I have a trailing 0 after a decimal, so that counts. How many moles of water is 5.02 times 10 to the 18 molecules of water? So I start with the number of molecules. I cancel it out because there's in 1 mole of anything, there's 6.02 times 10 to the 23rd. It's molecules, so moles. Molecules cancel, and I'm left with the number of moles of water. It makes sense that it's a very small amount because I don't have quite yet 1 mole. So how many formula units are in 15.2 moles of sodium chloride? So the reason why they use sodium formula units is sodium chloride, remember, it's not a molecule. So we don't want to really say sodium chloride molecules. It's a formula unit showing that it's a 1-to-1 ratio in that complex lattice structure, okay? But how many units of sodium chloride are in 15.2 moles? Well, in 15.2 moles of sodium chloride, 1 mole of anything is 6.0222 times 10 to the 23rd. I started with 3 sig figs. I end with 3 sig figs. I have 9.14 times 10 to the 28 atoms of cobalt. How many moles of cobalt? So this time I'm going to flip and I'm going to have the number of atoms. I need to cancel the number of atoms on the bottom. So the 6.022 times 10 to the 23rd goes in the bottom per 1 mole. And that leaves me with 1.52 times 10 to the 5 moles of cobalt atoms. And just kind of be funny, how many eggs are in 8.11 times 10 to the 6 moles of eggs? So in 1 mole of eggs, just like anything, there's 6.022 times 10 to the 23rd eggs. Remember, the unit that I want to cancel goes in the bottom of the conversion factor. I'm left with the number of eggs. I have 3 sig figs because I started with 3 sig figs for my final answer. So just remember, 1 mole of atoms of any element equals its atomic mass, right? So hydrogen, the atomic mass is 1.01 AMU, but if I want a mole of it, right, instead of, it's not useful to know the weight of 1 hydrogen atom, okay? I mean, because it's atomic mass units, it's like 1.67 times 10 to the negative 27 grams. It's not very, or kilograms, that's not very useful. Sorry, 1.67 times 10 to the negative 27 kilograms. So what I'd rather do is change this unit from atomic mass units to grams per mole, because I could weigh 1 gram on a scale, but now I've upped it to 6.022 times 10 to the 23rd. So if I want to know how much a mole of any element weighs, just look at the periodic table. You take the atomic mass and you change the unit to grams to mole, and that'll give you molar mass. It's really easy. So again, what does moles look like? Well, 1 mole of sulfur, which is 32.07 grams. How do I know that? On the periodic table, I see that the atomic mass is 32.07 AMU. I change it to grams to get moles. And now I can weigh it. So 1 mole of carbon is 12.0 grams. That's the molar mass. So what if I have a molecule, right? Because so far I'm just doing elements: hydrogen, magnesium, sodium, sulfur, carbon. What if I actually have a molecule? Well, I just add up the atomic masses of all the atoms and change the unit to grams per mole as well. So here's the periodic table. You always need it. This is an old school one. But let's say I wanted to know the molar mass of barium chloride. So in the formula, there's 1 barium. I find the molar mass of barium. It's 137.33 AMU. I change that to grams per mole because I'm looking for not 1 barium chloride formula unit, but a mole of it. There's 2 chloride. Each chloride is 35.45. Again, I'm recommending going to the hundredths place. 2 times 35.45 is 70.9. When I add these together, I get 208.23 grams per mole. So I would have to weigh out 208.23 grams to get 1 mole of barium chloride. Okay, so why is that important? Well, we should be able to calculate the molar mass of any formula, right? So NH4Cl, how would I get that? Well, there's 1 nitrogen. I would add 4 of the hydrogens, right? And then I would add 1 of the chlorines. Okay, and you should come up with, when you use a periodic table, 53.50 grams per mole. Same with the barium nitrate. Again, you got to refer to the periodic table. There's 1 barium. Then you're going to add that to, now notice there's a subscript 2 for each nitrate group. So that's 2 nitrogen plus, in the nitrate, there's 3 oxygen, but there's 2 of them, 6 oxygens. So what will that equal? So again, you're going to plug in for barium, the mass right here. For nitrogen, you're going to plug the mass right here. And for oxygen, you're going to plug the mass right there. And you should get 261.35 grams per mole. For aluminum sulfate, 2 aluminum, 3 sulfur, and then 12 oxygen. Okay, so it's like 2 times, I think it's 26 point, what is it? I mean, I'll just kind of break it down for you. Sorry, I'm getting 26.98. 3 times I look for sulfur, I think that's 32.06. And then 12 times 16. Figure out those products, sum them all up, and my total should be 342.17 grams per mole. Okay, so that's how you would calculate the molar mass of any molecule. You'll look to the periodic table, look at the form. This is why we need nomenclature and the ability to write out chemical formulas, because when we're calculating molar mass, we have to have the correct subscript so that we can calculate it correctly. Okay, so that's a big part of it. So what is the mass in grams of 4.82 moles of silver phosphate? Well, silver phosphate weighs 418.58 grams per mole. How did you do that? You looked at the periodic table and you said 3 times whatever the mass of silver is, plus 1 times the mass of phosphate. Whoops, it almost looked like a multiplication. Plus 4 times the mass of the oxygen. And now I know there's 4.82 moles. So I know that there's 418.58 grams per mole. I want to put the moles on the bottom so that the unit cancels. It does, and I get 2.02 times 10 to the 3 grams of silver phosphate. Now, there's 3 sig figs here, 3 sig figs here. Here's the thing. This calculation only involves one conversion factor, which isn't much. But if you don't know that silver phosphate is this formula, this won't be correct, and neither will this. So that's why nomenclature is important. How do we get this formula? Silver is always +1. Phosphate is a 3 minus. When we crisscross, we get the Ag3PO4. So this is where you start realizing, okay, I need to know that prior material. So what is the mass in grams of 0.00284 moles of zinc bicarbonate? So you got to get what? The mass in grams. How do you do that? Molar mass, which is grams per mole. If I have, if I have moles, I can convert that to grams using molar mass, grams per mole. But I need to know zinc bicarbonate. Zinc is 2+, and bicarbonate is HCO3 minus. When I crisscross, I need 2 bicarbonates, and then the molar mass, I can calculate it out, is 187.43 grams per mole. So now I begin with the 0.00284 moles of zinc bicarbonate. I want to make sure that moles goes on the bottom to cancel it. So I use the moles on the bottom. I got 187.43 grams on top. Those units cancel, and I'm left with 0.532 grams of the zinc bicarbonate. How many moles are in 28 grams of carbon dioxide? Now, the nice one about carbon dioxide, it's not ionic, it's covalent. So I don't need to worry about charges. I just need the prefixes. So it's CO2. So CO2 is 44.01 grams per mole. How did I get that? Right? There's 1 carbon, there's 2 oxygen, right? The 1 carbon is 1 times 12.01. The 2 oxygen is 2 times 16, 32, 12.01, 44.01 grams per mole. I start with 28 grams. I want to convert to moles. So I have to flip this conversion factor because that'll allow me to go to moles. So there's 44.01 grams per mole of CO2. Grams cancel, and now I know how many moles. And that makes sense. I don't have 44 grams, so I don't have quite 1 mole. There's only 2 sig figs. Why? Because 28. There's 2 sig figs. Why does this not count? It's leading. Leading zeros, zeros on the left, never count. Leading left, never count, ever, ever. Okay. How many moles are in 692 grams of iron 3 phosphate? So I'm sorry, I said iron 3, iron 2. Iron 2, so 2 plus phosphate. So I know phosphate has phosphorus and oxygen. To determine if there's 3 or 4, I look to see if phosphorus is on the floor. It is, so phosphate has 4, so phosphite must have 3. It's a 3 minus, so I must do a crisscross, and I get 3 of the iron 2, 2 of the phosphites. I multiply it, add up all the molar masses, and I get 325.49 grams per mole. I start with 692 grams of it. This is a ratio. I'm going to flip it and make sure that the grams are in the denominator so that I can cancel out the units, and I get 2.13 moles. Why? 3 sig figs, 3 sig figs. So what is the mass in grams of 51.2 moles of trichlorine nanofluoride? So the first thing you got to do is you got to figure out what is the formula of trichlorine nanofluoride. So tri means 3, so there's 3 chlorines. Nona means 9, so there's 9 fluorides. So now that I know the formula, I have to go to the periodic table and be like, here's chlorine, here's fluorine. The molar mass totals to 277.35 grams of trichlorine nanofluoride in 1 mole. I'm starting with 51.2 moles. So 51.2 moles of trichlorine nanofluoride, 1 mole is 273.35. The moles canceled. Remember, the unit you want to cancel goes in the bottom, and I'm left with 14,200 grams. Now, why do I have these zeros? I only need 3 sig figs, so this answer has 3 sig figs. These trailing zeros do not count because there's not a decimal. If you put a decimal right there, that would be 5. You would get sig figs wrong, okay? If you want to put it in scientific notation, you can do that. Times 10 to the 4 grams of CO3F. How did I do that? 1, 2, 3, 4. The exponent is positive because this number is bigger than 1. How many moles are in 189 grams of strontium phosphide? Strontium, SR2 plus, phosphide, phosphorus, P3 minus. So I go on the periodic table and I figure out 1 mole of strontium phosphide is 324.8 grams. I need to convert grams to moles. That's why if you see, I kind of flip this so that the grams are in the bottom to cancel out grams here. So 189 grams of strontium phosphide gives me 324.8 grams of strontium phosphide per 1 mole. Oh, I have 0.582 moles. That makes sense because this is roughly 1/2 or 60% of that molar mass. I have 3 sig figs because 189 is 3 sig figs. How many formula units are in 6.12 kilograms of lithium nitride? Okay, lithium nitride, lithium is +2, nitride is 3 minus. So when I crisscross, I get Li3N. But what's different here is I have kilograms, okay? Still need the periodic table because I know I want formula units. So I want to know how many. That's what Avogadro's number told me, right? In 1 mole of anything, there's 6.02 times 10 to the 23rd. So, but I need to know how many moles from mass. So what do I need? I need molar mass. So in 1 mole, there's 34.83 grams of lithium nitride. I need the metric system. Why do I need the metric system? Well, I have kilograms and molar mass. Remember, the unit is grams per mole, not kilograms. So I need to convert kilograms to grams. And then last but not least, I need to remember Avogadro's number. 1 mole of anything, if I want to figure out how many, the number of units, 1 mole of anything is that sweet, beautiful number, 6.022 times 10 to the 23rd. You'll memorize that, trust me. So now I set it all up in one clean, efficient conversion factor method, or you can call it I call it the railroad tracks here because I got my railroad tracks, and it's nice and efficient. I don't want to break this up into 3 separate calculations and risk round off errors, sig fig errors, and it takes a lot longer to write out. I set everything up. So I'm starting with the 6.12 kilograms. I want to convert kilograms to grams. So I use the metric system. That was this one. 1 kilogram, 1,000 grams. I want to convert grams to moles. That's how I can get to counting. So I use the molar mass. How? Periodic table. 3 lithium, 1 nitrogen. Use the periodic table, figure out the molar mass to be that. Grams of lithium nitride, there's 34.83 in 1 mole. But I didn't just want moles. I wanted the number of particles. 1 mole of anything, remember, it's like music to your ears. 1 mole of anything is 6.022 times 10 to the 23rd units, which is 1.06 times 10 to the 26 lithium nitride units. So that is a nice problem. That also shows me how I'm using multiple sections now. I'm using chapter 2, the metric system, converting kilograms to grams. I'm using chapter 2 for sig figs for my final answer and exponential notation. I'm using this chapter to determine molar mass and using Avogadro's number, which is chapter 7. I'm using chapter, what was it? 6 to change the name into the correct formula. So we're building it all together. It's beautiful. And just to give you an idea of how many points this would be on exam, this is 1 point, 2, 3, 4 points. So what is the mass in grams of 3.05 times 10 to the 24 gold atoms? Okay. So I need to know how much it weighs because I want to go to mass in grams. So I need this. So gold, 196.967. I also need that Avogadro's number. So I have this many gold atoms. If I want to change a number, so this is the number of atoms, to moles, how do I do that? Well, there's 6.022 times 10 to the 23rd gold atoms in 1 mole. And then using the periodic table, in 1 mole of gold atoms, there's 196.97. I always go to the hundredths because you don't want to waste time writing like 5 decimal places after. Just go to the hundredths, make it clean. Moles cancel. I'm left with 9.98 times 10 to the 3 grams of gold atoms. I have 3 sig figs because this. Could I change this to kilograms? Of course. There's 1,000 grams in 1 kilogram. So what would I do? That would mean I would basically divide it by the 10 to the 3 because that's what 1,000 is. So there'd be 9.98 kilogram of gold. That's a lot of gold, man. Solid gold. Ooh. Okay. So the mole is very useful. The mole allows us to count by weighing, and it allows us to look at subscripts and ratios. So what do I mean by that? 1 molecule of H2O, we know, because we've been drawing molecular geometry. Here's H2O, right? And it's got 2 lone pairs. There's 2 hydrogens and 1 oxygen. But again, we're not weighing 1 molecule. It's too small. So what are we going to do? We can weigh out 1 mole of H2O because it's, right, this is 1 molecule is only 18.02 AMU. There's no way you're going to put it on a scale. But a mole of water, there's 18.02 grams per mole of water. So in 1 mole of water, just a ratio. I have 2 moles of hydrogen, just because there's 2 hydrogen atoms per water molecule, and 1 mole of oxygen. So we could write this as several different conversion factors. So mole ratios is what we're working with because that's what we're using. There's 2 moles of hydrogen per 1 mole of water. There's 1 mole of oxygen per 1 mole of water, or in water, there's 2 moles of hydrogen per 1 mole of oxygen. So these are just conversion factors. So now, because I'm working with molar mass and I'm working with quantities in grams that are more realistic, when I look at a formula like carbon tetrachloride, I'm really thinking I got a mole of this. So if I have a mole of carbon tetrachloride, then I got a mole of chlorine atoms. It's just a ratio. There's 4 chlorines per carbon tetrachloride. So if I have 1 mole of this, I'm going to have 4 moles of this. It's a 4-to-1 ratio. How do I know that? That's what this subscript's been telling me all along. That's why the chemical formula is so important, because it tells me a mole ratio, and then I can convert that to grams, which allows me to quantify and weigh in a lab. So how many nitrogen atoms are in, 56.04 grams of dinitrogen tetrahydride. Okay, dinitrogen tetrahydride. The first thing is I need to know the formula. dinitrogen, di means 2, tetra means 4 hydride. Okay, so the molar mass for dinitrogen tetrahydride is 32.06 grams per mole. Why do I want to know that? I need to go from grams of this molecule to the number of atoms. So I can convert grams to moles, moles to the number of molecules, and then molecules to the number of atoms, or ratio. So here we go. There's 32.06 grams of N2H4 per mole. In 1 mole of N2H4, there's 2 moles of N. In 1 mole of N, there's 6.02 times 10 to the 23rd atoms. Now, there is another way to do this, and it's not wrong at all. In fact, I'm weird. I kind of like the unorthodox way. I like to say, all right, I have 56.04 grams of N2H4. There's 32.06 grams of N2H4 and 1 mole of N2H4. Now, don't get mad. Here I go. 1 mole of N2H4, there's 6.022 times 10 to the 23 N2H4 molecules. In 1 molecule of N2H4, there's 2 nitrogen atoms. And you see, I'm still doing 2 times 6.022 times 10 to the 23rd. And I still have 1 and 1 on these 2 bonds. Either way is fine. You end up getting the same number, as long as you have a logical way of following it. I like doing molecule to atom ratios versus looking at a formula and doing the molar, but it's okay. Either way is acceptable. So perform the following calculations. How many chlorine atoms are in 39.2 grams of strontium chlorate? So again, I need to know that strontium is Sr2 plus. Why? It's a metal, and I'm going with an oxyanion, so I need to go to the periodic table. I see strontium's 2 plus, because this is a ionic compound, because it has a metal. Chlorate, it's not on the 4, so there's 3, and I crisscross, and I get this, 254.52 grams of strontium chlorate, okay, for 1 mole. I want to know how many chlorine atoms. All right, well, there's 39.2 grams of strontium chlorate to begin with. There's 254.52 grams of strontium chlorate per 1 mole. And you could do it the mole ratio way. In 1 mole, there's 2 moles of chlorine, and I get that because of this, right? So when I crisscross, there's 2 chlorates. Each chlorate has 1, so there's 2 chlorines. And 1 mole of chlorine, there's 6.02 times 10 to the 23rd. Now, there is another way. You could say 39.2 grams of strontium chlorate. There's 254.52 grams per 1 mole of strontium chlorate. In 1 mole of strontium chlorate. Instead of doing a mole ratio, you can just say there's 6.022 times 10 to the 23rd formula units of it. F you. We'll just say units. And then in 1, formula unit of strontium chlorate, there's 2 chlorine atoms. So it's the same way. You'll get the same answer. It's just another option. Either way is acceptable, whatever. Now, some students are like, you're confusing me. I don't like this way. Okay, don't do it. If you prefer this method and it works for you, use this method. Use it every single time. never do this method. I'm just showing you there's more than one way to solve a problem. What is the mass in grams of xenon hexafluoride containing 40 grams of fluorine? Okay, so xenon hexafluoride. The reason why it's hexa is non-metal, non-metal. I need a prefix because this is a covalent compound. When I calculate it out, I see that for the molar mass, the total is 245.3 grams per mole. But for this, I can just do a mass ratio. What is the mass in grams, right, of a xenon hexafluoride sample containing 40 grams of fluorine? Well, in xenon hexafluoride, if there's 114 grams of fluorine per 245.3 grams of xenon hexafluoride, I can just do that ratio. I could say, well, I have 40 grams of fluorine, 19 times 6, which is the 114 grams, right, per 245.3 grams of xenon is 86 grams of xenon fluorine. The other method is to do the, the mole ratio, which you could do as well. I think this is cleaner. So what is the mass in grams of copper 1 sulfate sample containing 2.03 times 10 to the 23rd atoms of copper? So copper, I think I said copper 2. I'm sorry, copper 1 sulfate. So you need to know the formula. So it's copper 1 sulfate. So I determine the molar mass using the periodic table. I'm starting with 2.03 times 10 to the 23rd copper atoms. In 1 mole of anything, there's 6.02 times 10 to the 23rd copper atoms. 1 mole of copper, but in copper 1 sulfate, there's 2 moles of copper per 1 mole of copper 2 sulfate. So there I use the mole ratio, 1 mole of copper to 2 moles, 2 moles of copper, 1 mole copper, 1 sulfate. And in 1 mole of copper 2 sulfate, there's 223.14 grams of copper 1 sulfate. 3 sig figs for my final answer, because I have 3 sig figs here. So why are we calculating molar masses and mole ratios? Well, the reason why we're doing that, the reason why we balance chemical equations is those coefficients in balance equations were actually mole ratios. And basically a chemical reaction, in a way, you can think of it as kind of following the recipe. What do I mean? Well, if I have a certain recipe, if I follow it, I'll get a certain amount of product. So if I start with each of these reactants or ingredients, it should produce a certain amount of product, cookies. If you don't follow the ratio, you won't get the desired amount of product, right? If I change this around, I won't get it, okay? So it's very critical to know how much I have to figure out how much I'm going to end with, or if I want to end with a certain amount, how much I need to start with. And if I alter that, it won't come out right. So just like bakers, chemists, engineers, we got to perform these reactions. This is basically what stoichiometry is. It's determining how much of something can be produced, okay? So these calculations are used to avoid excess amounts of costly chemicals. We don't want a bunch of excess. We want efficiency. So we don't want a bunch of leftover product and then have to dispose of it. So we have to use stoichiometry. So again, these are called stoichiometric calculations. So how can you do this? You need balance equations for the reactions, and you need to know molar mass. So when I look at this equation, right, I have nitrogen monoxide with oxygen to nitrogen dioxide. Really, you could think of the twos, as molecules, or a better representation, instead of molecules, I can kind of just look at it as this is a 2 to 1 to 2 ratio. you can change the two molecules to 2,000. And then the one would be 1,000 and the two to 2,000. But in reality, that's still a small number of atoms. So what are we going to do? 2 moles. So 2 times 6.02 times 10 to the 23rd is this. 1 times 6.022 times 10 to the 23rd, and 2. This is better. Why? Because I can weigh out a mole of these molecules by simply looking at a periodic table and changing the unit to grams. So that's what we're going to be doing. We're looking at these coefficients as mole ratios with one another, and then we can take our periodic table and calculate molar mass to figure out how many grams of each. So we can now read the above balanced chemical equation as 2 moles of nitrogen monoxide gas react with 1 mole of oxygen gas to produce 2 moles of nitrogen dioxide gas. These coefficients give us a ratios of moles, which in stoichiometry is kind of the centerpiece, and we call that the mole ratio. And that's why the earlier part of this chapter, balancing equations, is critical, because we need to have the correct mole ratio. That's also why in the earlier chapter 6, knowing the correct chemical formula is critical, because if you don't have the correct formula, you won't be able to balance it correctly, and then you won't get the right mole ratio. So we see that everything's kind of building at this point. This is when we're really, I call it the nitty-gritty of chem. We're like studying reactions. We have a good foundation and we still have a decent amount left, but we're starting to solidify and piece everything together and build on our existing knowledge. So we can use a balanced chemical equation to write mole ratios. So in this reaction, it's 1 mole of nitrogen gas, 1 mole of oxygen gas, 2 moles of nitrogen monoxide gas. So look at all the ratios. There's 1 mole of nitrogen to 1 mole of oxygen. So I need 1 mole of this reactant to react with that. I could flip this if I need to. It's a conversion factor. 1 mole of N2 produces 2 moles of NO. And I can flip it. 1 mole of O2 produces 2 moles of nitrogen monoxide. So there's quite a few calculations that we can use, stoichiometric calculations, with a balanced equation. So there's 2 common ones, mole to mole for this class, and grams to grams. However, there's more than just this. I mean, I'll be honest. You can convert grams to the number of molecules of atoms, because we learned just using mole that if we convert grams to moles, then we know in 1 mole, there's 6.02 times 10 to the 23rd. So we could do that as well. We could also change grams to kilograms. So here, if we wanted to go one step further, we could go to kilograms. But again, the focus is let's get this down so all the other information is a little bit easier. So let's start with just mole to mole. If I have 2.25 moles of nitrogen, how many moles of oxygen will it react with? Well, we want moles of O2. We have moles of N2. We know it's a 1-to-1 ratio. We set it up. I start with the 2.25 moles of N2. I need this to cancel, so this has to go on the bottom. And I know from the balance equation, 1 mole of N2 reacts with 1 mole of O2. So I would have the 2.25 moles of O2. And I know you're thinking that's easy. It's not always that easy, but this one is easy because it's a nice 1-to-1 mole ratio. Not all of your balance equations are going to have 1-to-1 mole ratios. So here's an example where you don't, right? So octane is the major. In the very beginning of chapter 7, I talked about the combustion of octane. It's a major component in gas. And we can write out the balanced chemical equation to this combustion reaction. How do we know this is combustion? We have oxygen as a reactant. We produce CO2 and water. Is this balanced? Well, let's see. We have 8 carbon here times 2. that's 16. We have 16 here. We have 18 hydrogen times the 2. So 18 times 2 is 36. 18 times 2, 36. And then we go to the oxygen. 25 times 2 is 50. So 16 times the 2 here is 34, right? Plus, oh, I'm sorry, I said 34, 32. I'm tired. 32 plus 18 is 50, and that works. So this is balanced. So what does that mean? Now that this is balanced, I can predict mole ratios. And if I can predict mole ratios, I can do mole to mole calculations. So how many moles of O2 are needed to burn 1.25 moles of octane? So my mole ratio, I want moles of O2. Well, there's 25 moles of O2 needed to burn 2 moles. So I'm just using the coefficients of octane. So now I start with the 1.25 moles. I make sure to have on the bottom the moles of octane. And then on the top, I have moles of O2. These cancel, and I'm left with the 15.6 moles of O2. Let's try another one. How many moles of C8H18 or octane are needed to produce 5 moles of CO2? So now I'm going octane to CO2. How do I do that? Well, there's, 16 moles of CO2 per 2 moles of octane. What am I starting with? Okay, well, I'm starting with 5 moles, 3 sig figs of CO2. Now, the way I wrote this ratio, where did I get 16 CO2 to 2? I need to get the CO2 moles to cancel. So that needs to go on the bottom. And I'm going to moles of octane. That has to go on top. But what you never want to do is write 1 to 1, because it's not. So people do that a lot. The ratio is I need 2 moles of octane to produce 16 moles of CO2. Where am I getting it? The balanced chemical equation. So now what do? Moles of CO2 cancel. I'm left with moles of octane. And my final answer is 3.13 moles of octane. So what do you need for Stoich? You need a balanced chemical equation. So in the homeworks, sometimes they give it to you, sometimes they don't. But for the most part, it has to be balanced. So if it's not given, you're going to have to balance it. That's step 1. If you have the balanced equation, if they give you grams and you're doing stoichiometry, and you'll know that you're doing stoich because they'll give you a reaction and they'll ask for a certain quantity of one of the things, one of the substances in the reaction. So if they give you units of grams, convert it to moles. If they already give you moles, then you don't need to worry about it. You already have the moles. And like we just did, once you have the moles of whatever it is they give you, you can convert it to the moles of what you want. That's that mole ratio that we just did. We just did that right here. There's a 2 mole to 16 mole ratio between the CO2 and the octane. So that's your mole ratio. That is the centerpiece. But in some cases, they might ask for grams. How many grams? So then you'll have to convert moles to grams. And how do you do that? Molar mass. So typically, not always, the path is grams of whatever they give you, you convert to moles. How? Molar mass, using the periodic table. Then you go from moles to moles. How? The balanced equation in your mole ratio. And then once you have the moles of what they're asking for, if they do ask for grams, again, you're going to use molar mass. Okay. So if I have 1.334 moles of octane, so I'm still on octane, high octane here, 1.334 moles of octane, and it reacts with oxygen, how many grams of carbon dioxide? Okay, so they want grams of this, and I start with moles of this. Okay, so I'm not really starting with grams of octane. I'm starting with moles. That's why I'm saying it's mole to gram. So what do I need to do? Well, I need a mole to mole relationship because I have this is my given, 1.334 moles of octane. But I want to get to CO2. Well, how can I do that? Well, how many moles of octane react to give me moles of CO2? Well, what do I do now? Well, what do I look at? I know this probably clean this up a little bit. 2 moles of octane are going to produce 16 moles of CO2. So that takes care of my given moles of octane, right? And now I have moles of what I want. I want CO2. If they only wanted moles of CO2, I'd be done. That was those other problems we just did. But they want more, of course. They want grams. So how do we do that? Well, CO2, I can figure out the molar mass. And I can say, well, wait. 1 mole of CO2, why am I putting this on the bottom? To cancel out moles of CO2 is 44.01 grams of CO2. So I'm canceling out the units, but do not cancel out the numbers because they're not the units are what's canceling, okay? So when I do that, again, I'm canceling out just the moles of C8H18, the moles of CO2, and I'm left with grams of CO2. And I have 4 sig figs because that's what I initially started with, 4 sig figs. So that's mole to gram. Could we do more? Yeah. Remember, I said 2 common ones are mole to mole, but the other common one is gram to gram. But you can't go directly gram to gram because the substances weigh differently and you have different amounts. But what you can do because of your balanced equation is use your coefficients to get mole ratios and then convert to grams. So how do I do this? How many grams of glucose? So I'm looking for grams of glucose. This is glucose. This is what I want. Can be synthesized from 58.5 grams of CO2. So I have 58.5 grams of CO2. So I'm going to write that right there. Right? But grams of CO2 doesn't equal grams of, glucose. But what I can do is I could say, well, when I produce 1 gram of glucose, it requires 1 mole of glucose. When I produce 1 mole of glucose, I need 6 moles of CO2. So I know that I have a 1 to 6 mole ratio. So what I can do is I can convert the grams of CO2 to moles. Get to that mole ratio. That's what the balance equation does for me. That's the centerpiece of stoichiometry. So now I can say, all right, I can go from grams of CO2 to moles of CO2. And in 1 mole of CO2, how do I figure out how many grams? Molar mass. That's what we were doing earlier, periodic table. There's 44.01 grams of CO2 in 1 mole. Excellent. I've just gotten rid of grams, and now I'm on moles of CO2. but I don't want CO2. I want glucose. So now I'm going to convert moles of CO2 to moles of glucose. How do I do that? Well, there's 1 mole of glucose in this equation to 6 moles of CO2. So now I cancel out the units of moles of CO2 and I have moles of glucose. If they only wanted moles of glucose, I'd be done. They don't. They want grams. So what do? Well, in 1 mole of glucose, can I figure out how many grams? Of course you can. The best cheat sheet in the world is roughly 180 grams of glucose in 1 mole. So now the moles cancel. I'm left with grams of glucose. And I get 39.9 grams of glucose. And why is that? Because there's 3 sig figs and there's 3 sig figs. That's stoichiometry. So this is a good time to pause and try to figure this out. Like, how many grams of O2 are needed to burn 10 grams of octane? Okay, so what's going to be your path? Well, I have 10 grams of octane, right? And I convert grams of octane to moles. Now, why is that? Because 2 moles of octane react with 25 moles of O2. And once I have moles of O2, I can use the molar mass to convert that to grams of O2. So that's how we're going to do it. 10 grams of octane I have to figure out the molar mass of octane. That would give me 1 mole of octane. So how do I do the molar mass? Periodic table. Let me do that real quick. Sorry, I don't memorize this stuff. So 8 times 12.01, because the carbon is 12.01 on the periodic table, there's 8 of them, plus 18 times 1.01, or the oxygen, it's about 114.26 grams of octane per mole. So the grams of octane cancel. Then there's 2 moles, where'd I get that, of octane that react with 25 moles of O2. So moles of octane cancel. But I want grams of O2. So 1 mole of O2 is, look up the periodic table, 2 times the mass of oxygen, which is 16, 32 grams of O2. And I get my answer, 35.0 grams. 3 sig figs. Why? These trailing zeros count because there's a decimal. This trailing zero counts because there's a decimal. It all builds. So what about 14? Ay, 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 what are you doing? What are we doing here? What did they not give me? What did they not give me? And how do, first of all, if I read this, how do I even know this is stoichiometry and I need a balanced equation? Calcium hydroxide reacts with silver nitrate. Reaction, chemical equation to produce calcium nitrate and silver hydroxide. If I start with 10 grams, they're giving me a quantity in a reaction. How many grams of silver will be produced? They want a quantity that's produced. Classic stoic. They give me a quantity that I start with in a reaction. How much do I produce? Because I want efficiency. The problem in this one is, what did they not give me? They did not give me the reaction. Calcium hydroxide, right? Silver nitrate, silver is +1, nitrate. I have to figure out the formulas. So what did I do here? Crisscross. There's 2 hydroxides to 1 calcium. There's 1 silver to nitrate. Why are these aqueous? Right? Calcium hydroxide is a base, it's aqueous. Nitrates are always aqueous. It reacts to do what? Produce calcium nitrate, Ca2 plus, NO3 minus, silver hydroxide, Ag plus, OH minus. So when I do that, I end up getting crisscross, 2 nitrates to 1 calcium. This is a 1-to-1 ratio, and this is my precipitate. Silver is a heavy metal. That's going to be my precipitate. By the way, this is a double displacement. This is a double displacement. How do I know? Compound, compound, new compound, and more specifically of a double displacement, it's precipitation because the solid was formed. How could you do this? How could, if I had given you these formulas, how could I predict the products if it wasn't given? Because I actually give the products, produce calcium nitrate and silver hydroxide. Well, that's easy. Calcium 2 plus, OH minus, silver nitrate, do-si-do. And then when I do-si-do, I would see I need 2 nitrates to 1 calcium and 1-to-1 for silver and hydroxide. So it all starts to build, okay? So now that I have the correct formulas, I need to balance it. Who do I balance first? Metals. 1 calcium on the reactant side, 1 on the product. 1 silver, 1 silver. Good. Then I have 1 nitrate on the reactant, but 2 over here, so I need to put a 2. Uh-oh, I put a 2 in front of the silver, I got to put a 2 here. Uh-oh, there's 2 hydroxides. Oh, wait, I'm balanced. So now I have my balanced equation. Why do I need a balanced equation? Because I have to have the correct mole ratios. Now what am I going to do? I'm going to go from grams of calcium hydroxide. So I have 10 grams of calcium hydroxide. I need to go to moles. Why? Because once I know moles of calcium hydroxide, I can figure out how many grams of silver hydroxide are produced. So now, how do I do that? If I know that I have moles of calcium hydroxide, I can get moles of silver hydroxide. And once I have moles of silver hydroxide, I can figure out grams. So when I write it out, I have 10 grams of calcium hydroxide. The molar mass using the periodic table for calcium hydroxide is 74.1 grams per mole. Grams cancel. 1 mole of calcium hydroxide. To cancel that, I use my mole ratio. There's 1 mole of calcium hydroxide to 2 moles of silver hydroxide. So 1 mole of calcium hydroxide to 2 moles of silver hydroxide. Now the unit of moles of calcium hydroxide cancel. Now I need to convert moles of silver hydroxide to grams. How? Molar mass. 1 mole of silver hydroxide, that cancels out that unit, is 124.88 grams. I do the calculation. My final answer needs to have 4 sig figs, and it does. Okay. This time, I'll give you the balanced equation, but we're going to change it slightly. Instead of giving you grams, we're going to start with kilograms. Okay, so I have kilograms of Fe2O3. Now, how do I know this is even stoic? An iron ore sample contains iron 3 oxide together with other substances. The reaction of the ore with carbon monoxide produces iron, the metal. Calculate the number of grams of carbon monoxide that can react with this many kilograms of Fe. So this is stoic. They give you a reaction, right? And then they tell you this quantity is going to help me determine an unknown quantity. So you're given a quantity and you have to determine an unknown quantity. So what do you have to convert the given quantity to? Moles. How am I going to do that? Well, I'm going to convert kilograms to grams. How? The metric system. I'm going to convert grams to moles. How? Molar mass, periodic table. I'm going to convert moles to moles. How? Mole ratio. There's 1 mole of iron 3 oxide to 3 moles of CO. They don't want just moles of CO, they want grams. That's okay. I can go to grams of CO. How? Molar mass. So when I do that, I convert the kilograms to grams using the metric system. 1 kilogram is 1,000 grams. Kilograms cancel. I convert the grams to moles for iron 3 oxide using periodic table, molar mass. We've been doing this, right? So there's 159.7 grams of iron 3 oxide per mole. The grams unit cancel. I used a balance equation to show me 1 mole of iron 3 oxide is 3 moles of CO2. So I need to get rid of mole, this unit, moles of iron 3 oxide. So I put it on the bottom. It's a 1 to 3 mole ratio. That unit cancels. And now that I have moles of carbon oxide, what do I need to get? Grams. How do I do that? Molar mass. In 1 mole of carbon oxide, there's 28.01 grams. Moles canceled. I'm left with 3 sig figs. Stoichiometry. This is the building block of this class. We will not only do, this is referred to as gravimetric stoich, where gravity, you're weighing things using masses, grams. When we do gas laws, we'll do gas stoichiometry. When we do solution chemistry, we'll do solution stoichiometry. So this chapter is critical because we do a lot of stoichiometry. We do a lot of reactions and then predicting when we start with this much, how much do we end? This is like the centerpiece of the course, and it makes sense. It's kind of in the middle of the course. Calculate the number of grams of iron and the number of grams of CO2 formed when there's 0.150 kilograms of iron 3 oxide that reacts, okay? So I have kilograms of this. Again, I'm going to convert it to grams, convert it to moles. Once I have moles of this, I can get moles of CO2 and moles of iron. Once I have moles of each of these, what can I do? I can convert these to grams. How do I do that? Molar mass. How do I go from mole to mole? Mole ratio. How do I go from kilogram to gram? Metric system. So we'll start for iron. 0.150 kilograms of the iron 3 oxide. 1 kilogram is 1,000 grams. There's 159.7 grams of iron 3 oxide per 1 mole. Grams of iron 3 oxide cancel. Using the balance equation, 1 mole of iron 3 oxide produces 2 moles of iron. So 1 mole of iron 3 oxide produces 2 moles of iron. That unit cancels. Go to the periodic table. 1 mole of iron is 55.85 grams of iron. Mole unit cancels. I'm left with grams. I do the same exact thing, except the difference is going to be this second half. Why? I still have to convert kilograms to grams, grams to moles, but then I'm going to have 1 mole of iron 3 oxide, and I'm going to convert it to 3 moles of CO2, and then 1 mole of CO2 is going to be what? 44 grams. So exact same setup. Convert the kilograms to grams using the metric system. Convert the grams to moles using molar mass in the periodic table. Convert moles to moles using a balanced 1 mole to 3 mole ratio. That cancels. Convert moles to grams. How? Again, the periodic table. That cancels. And then I get my final unit, final answer, 3 sig figs. So that's a doozy. And I totally get it. So if you need to stop, record, take breaks, please do it. The good news is everything you've learned in this 3rd lecture, we will continue to exercise and practice and get efficient and good at for the next lecture. And the last lecture for chapter 7, reactions and quantities in reactions, is going to be more stoichiometry, but we're going to understand that we don't have perfect ratios all the time. And there's something called a limiting reactant. And then there's a percent yield calculation to determine efficiency of technique and reactions. So I want to thank you for your patience. Yeah, I'll see you next lecture when we start discussing what I refer to as a double stoichiometry. And this is where we really perfect our system and get more and more fluid by doing more and more practice. But again, as always, thank you for watching and thanks for your patience. I appreciate it.